Well, there's a lot of chemical reactions that do not occur in confined spaces. They're open to the atmosphere. So the pressure is constant, but the volume can change. So there we have heat and work being done. But often, we're only interested in the heat. We don't care about the work. That pressure volume work, it didn't do us any good, and so we just don't really care about it. Well, we can't call the heat the change in internal energy. So we call this enthalpy instead, and that's a funny word. Enthalpy, and its symbol is H. So enthalpy is defined as the internal energy of that system plus the pressure times the volume. So H equals E plus PV. Well, that's not so helpful. Enthalpy is a state function. It kind of has to be because internal energy is a state function, pressure is a state function, and volume is a state function. And since enthalpy is a combination of those, it's a state function. Remember, a state function is something that depends on where it is now. And if you're going to look at a change in a state function, it's where it started, where it ended up. How it got there doesn't matter. Okay, so enthalpy is a state function. Well, like with lots of things, we can't measure the actual value of enthalpy, but we can measure enthalpy change. So the enthalpy change is the heat evolved at constant pressure. So delta H is going to then be equal to delta E plus P delta V. We don't put a delta in front of the P because the pressure isn't changing. Well, P delta V looks like work, doesn't it? Remember how we defined pressure volume work? Pressure volume work equals negative P delta V. So we previously said that delta E was Q plus W. Now we put a P on here because it's not the volume that's being held the same, it's the pressure that's the same. So delta E is Q plus W, and then we've got this plus P delta V. Well, P delta V is equal to negative W. And so we end up with QP plus W minus W. And so delta H comes out to be the heat exchanged at constant pressure. So the enthalpy change is heat at constant pressure. Any questions? I'm not going to make you derive that on an exam, but I think it's helpful to see where it came from. Now, delta H and delta E are not the same thing, right? They're not the same thing because there's that PV term in there. But they're often similar in value, and they're definitely very similar in concept. So delta E is the change in internal energy. That measures all the energy, heat, and work that are exchanged with surroundings. Delta H measures only the heat exchanged, and this is at constant pressure. Constant pressure, though, is very easy to obtain. That's what we were doing in our coffee cup calorimeters. It was open to the atmosphere, so the pressure stayed the same. The only time we really notice a big difference is when we have reactions that produce or consume large quantities of gases. If there aren't large quantities of gases either being, consumed or released, then it really doesn't matter that much. Delta H follows the same sign conventions as delta E. Delta H being positive means that heat's being absorbed into the system. That's an endothermic, endothermic reaction. Endo going in, heat going in. Delta H is negative, heat's being released, that's an exothermic reaction. Same sign convention. So we talked about chemical heat packs at the beginning of the chapter, iron filings that are oxidized in an exothermic reaction. Your hands get warm because energy is being released into the surroundings. The reaction is the iron filings. They're releasing energy. Your hands are part of the surroundings. There are also chemical cold packs. These generally have ammonium nitrate. And when that is exposed to water and begins to dissolve in water, it's an endothermic process. It absorbs energy from the surroundings. If your hands are in contact with that pouch, you feel the pouch sucking energy out of your hands, and you interpret that as cold. In a flame, we have an exothermic process where heat is being released into the surroundings. So identify each of these as endothermic or exothermic and indicate what the sign of delta H would be. An ice cube melting. So the process of the ice cube going from a solid to a liquid, is that taking energy in or releasing energy out? It's taking energy in, and so is it endothermic or exothermic? Endothermic. So this is endothermic, and what's the sign of delta H? Positive. Because I feel positive when money comes into my wallet, right? Nail polish remover quickly evaporating after it is accidentally spilled on the skin. So if this has happened to you, girls, most likely, how does it feel? It feels cold, right? It feels the same as if you spill alcohol on your skin, or if you've ever gotten an immunization and they take that alcohol swab and they wipe your arm, it feels cold, right? Because the alcohol is evaporating. That's also an endothermic process. It takes energy in to convert from the liquid to the gas state. Sometimes it's helpful when you're trying to evaluate something like this to say, okay, we have a state change. It's evaporating, going from a liquid to a gas. If I were trying to do this to water, would I have to heat it up or cool it down to cause this to happen? If I want water to evaporate, I'll put it on the stove and turn the burner on, right? I'll put energy into it. And so this is also an endothermic process. And then, just like the endothermic process up here, delta H has to be positive. How about gasoline burning within the cylinder of an automobile engine? Your clue here is burning. Exothermic. Any combustion reaction is an exothermic reaction. And so then delta H is negative. Does that make sense? Ooh, I got some nods. Let's think about this on the molecular level. Exothermic reaction gives off thermal energy, causes the temperature of the surroundings to rise. Where does the thermal energy come from? Well, it comes from the chemical potential energy stored in the reactants. We talked about positional potential energy, where something is lifted high up, it has higher potential energy. We also have chemical energy, a form of potential energy, has to do with the positions of the particles within the atoms and also the relative positions of atoms and molecules within the substance. So the potential energy that was stored in the reactant is being released into the surroundings as heat energy. We have existing bonds being broken and new bonds being made. When you have an exothermic process, the bonds that were broken had greater energy than the bonds that are being formed. And so that extra energy is released into the surroundings as heat. Endothermic reaction is the opposite. The temperature of the surroundings is going to go down because the reaction is absorbing heat energy from its surroundings, causing the surroundings to decrease in temperature. So again, we've got existing bonds being broken, new bonds being made. In an endothermic process, though, the products end up with more chemical energy than the reactants did. The new bonds that are being formed store more energy than the bonds that were there before. And they get that energy by sucking it out of the surroundings. Does that make sense? So enthalpy, back to enthalpy. The enthalpy change for a chemical reaction is symbolized as delta H for change in enthalpy, RXN, that's the chemist's abbreviation for the word reaction. So this is called the enthalpy of reaction, or often we just call it the heat of reaction. Right? Heat of reaction, heat and H makes sense, enthalpy is a weird word. This is an extensive property. It depends on the amount of stuff that is undergoing reaction. If you burn a teaspoon of gasoline or a bathtub full of gasoline, is there going to be a difference in the amount of energy released? Yes, very much so. Extensive properties depend on how much stuff you have. Mass and volume are extensive properties. So by convention, when we calculate delta H reaction, the heat of reaction, just by convention, we do it for the molar quantities in the reaction. So here's this chemical reaction. Pentane. No, not pentane, propane, sorry. Propane combusting, reacting with oxygen, making carbon dioxide and water. When we report this heat of reaction, this quantity, 2,044 kilojoules, is for 1 mole of this, because that's the coefficient in this equation. It's for 5 moles of oxygen. It's for 3 moles of carbon dioxide. It's for 4 moles of water. And we chose to do this because people thought it was convenient. And it is. But there's no magic to it. We just decided to do it that way. So 1 mole of propane, I don't know why, pentane, propane today are the same to me. 1 mole of C3H8 will release 2,044 kilojoules of energy when it's burned. 5 moles of oxygen undergoing this chemical reaction will release that amount of energy. So we'll often see a chemical reaction with a delta H over here. And this refers to the quantities specified here in moles. Okay, so ammonia reacts with oxygen according to this equation. We're supposed to calculate the heat in kilojoules associated with the complete reaction of 155 grams of ammonia. Well, this comes down to stoichiometry. We have a chemical reaction. We have an amount of one of the reactants. So we have 155 grams of ammonia. And we want to know how much heat is released when that reacts. This is the amount of heat released when 4 moles of that react. We have 155 grams. So we need to do some unit converting here. We're starting with grams of NH3. And we want to end up with kilojoules. This kilojoule amount is for 4 moles of that. So if we knew the moles of NH3, we could figure out how many kilojoules. Well, we know how to do molar mass calculations, and so if we have grams, we can convert to moles. Now, this is a little bit of a shortcut because we don't have to go grams to moles to moles to grams, because this relates directly to molar amounts of any of these. So there's still moles involved, but we just have to look at the one substance. So 155 grams of ammonia times moles of ammonia, and it'll be divided by grams of ammonia, so those units cancel out, and times, and we're going to have kilojoules on top and moles of ammonia in the bottom, so those units cancel out. This delta H is telling me minus 906 kilojoules for 4 moles of ammonia. 4 moles of ammonia, negative 4, no, I was remembering something else, 906. I put the parentheses around that just to kind of call attention. There is a minus sign in there. And then we need this molar mass here. Nitrogen plus 3 times the mass of hydrogen. 17.034. So 17.034 grams to 1 mole. So it's 155 divided by 17.034 times negative 906 divided by 4. So this is going to be negative, of course, 2061. We've got 3 sig figs here, 4, 3, so this is going to be 3 kilojoules. So you could express this as minus 2060 kilojoules, but better would be minus 2.06 times 10 to the third kilojoules. This is saying calculate the heat associated. The negative sign here is important because that tells us that energy is leaving, that this is energy that's being released. Any questions?